I'm very happy to welcome everyone back to the Colchian seminar on differential algebra. And today we are very happy, and I'm very happy to announce the talk by Emilie Dufresne, which is about structural and practical identifiability of ERK kinetics. Thank you very much for accepting our invitation.
Well, thanks for the invitation, and thanks for being here today. So for those of you who were at DART in London in the summer, this will be, well, not the same talk because it's online, so it's different, but it's on the same topic. So what I want to talk about is about joint work with Lewis Marsh, Ellen Byrne, and Heather Harrington, and on which looks at this, and it's a mathematical look at something that was done by Jung and al, into which Lewis, Heather, and I contributed before. So the thing, so there will be some differential algebra, but it's very much an application, and that is the motivation for the whole talk. So, oops, oh no, that's what I forgot to check. Just a minute. Huh? Whoops. Okay, sorry.
No problem.
It was doing beeps and stuff. So, okay, so what was I saying? Oh, yes. Let me pass to my first slide. Okay, I think just a second, I cannot see everything. Okay, so first I want to present to you the model and experimental setup of Jung and al. So what they're looking at, well, the basic idea is that in systems biology, dynamics play a big role in cell decision making. And this is modeled with chemical reaction networks, so something like that's in the corner, with the choice of kinetics. In this case, it's going to be mass action, which has a bunch of assumptions, including that you have so many things that it's almost continuous and that everything is very well mixed. And what they looked at is the dual phosphorization of ERK by MEK. And this is something, so these are two molecules, two molecular species whose activation regulates cell specialization, cell division, and cell death. And this is something that's of interest to biology. Okay, so we have here the chemical reaction network, and it involves two main things. So the E and the S's. The E is the MEK one of the MEK variants, and the S's are this ERK. And in between, I have two intermediate complexes that are formed and transformed, but which I won't be looking at. And my parameter space is going to be just the rate constants of the transformation of the chemical reactions here that I have in my graph. And Jung and al looked at data from this system for a number of variants. So there is the wild type, which is the one that occurs naturally. And then there's another four variants. So the first one here, E200 and K, is something that's involved with cancer. The next two have to do with development abnormality, so developmental problems. And then the final one, this SSDD, is a synthetic one that's often used as an approximation of wild type. And then I've got my initial conditions. So I have only to start with some of the S0, so 5 micromole, and some of the E, 0.65 micromole. So assuming mass action kinetics, I can turn this chemical reaction network into a no. Okay. I don't know why, but it's not turning page.
Could it be it's a question of which window on your computer has the focus, so to speak? So which one is the active window? Is that maybe the problem?
Ah, there it is. Okay, I don't know what is the problem, but now it's this one. Okay, so we've passed to the second one. So I've got here the system of ODEs. So that's a nonlinear ODEs in 6 variables with 6 parameters. And there's a couple of conserved quantities, which are very much linear relations in between the lines here. And I'm adding some extra bit of data. So the data will be measurement at the following time points. So there's 7 time points in all cases, but for the SSDD, the time points are different than for the other variants. And then the number of replicates, so the number of times that this experiment was conducted, so 11 times for wild type, 6 times for SSDD, and 5 for the other 3. So that's the setup. And we're going to focus, so in the paper, we talk about we eventually do the Bayesian inference, so from the data to get the parameters. But in this talk, I'm going to concentrate on the structural identifiability question. But first, one thing that people often do in this kind of setup is to reduce the model. And one kind of reduction that's very popular is called quasi-steady state approximation. So the idea with quasi-steady state approximation is that at some timescales, the rate of change of some variables is negligible. And so it's as if these were at steady state. And at first, this was done with heuristic arguments based on fast and slow reactions with some assumptions. And this was first done by Henri and then Michaelis-Menten in the 1910s and Briggs and Haldane in the 1920s. But at that point, it was still very somewhat end-wavy and based on intuitive knowledge of what's going on. It was made, but this can be made rigorous. And the classical way of making this rigorous is called the singular perturbation approach, which was done by Heineken et al. In the 1960s, and then Segel and Slemrod, and Schauer and Heinrich in the 1980s. And there's a much newer algebraic approach developed by Göke and Balchar in 2014, and then Göke et al. And this one is the one that we've selected because we're interested in algebra and geometry and this kind of stuff. But you'll see in the next slides that it does have some advantages. And what this approach gives you is an explicit formula for the quasi-steady state approximation model and a characterization for parameters for which the approximation is accurate. So meaning that the trajectories of the solution of the new systems are close in some precise way to the trajectories of the solution of the original system. So let's see what we get with our full ERC model. So if you do the algebraic QSSA for the full ERC model using the one of, so you first do a reduction, an exact reduction using one of the conserved quantities. So, and if you start with this conserved quantities and you apply the process, you end up with this new model that I've written down, which is rational now, and as now one less parameter. So we have 5 parameters. So 2 of the kappas and 2 of the gammas, and then pi. And yeah, so it is somewhat smaller, fewer variables, and now we measure everything. And alternatively, if we use this other conserved quantity, we now get a linear, what I call the linear ERC model. So a linear model with 3 variables. And that's nice because then there are exact solutions and it's simpler. And one thing to mention is the first one here, the rational ERC model, is what you would get from the singular perturbation approach. This one, the linear ERC model, you don't get. But this was the model this was a reduction that had been performed in the paper by Jung and al. In that paper, it was done based on heuristic argument and additional assumption because it seemed to fit the data. And using this algebraic quasi-steady state approximation, we can say that this reduction is justified mathematically. And so now we end up with 3 potential model to so we end up with 3 potential models: the full arc model, the rational arc model, and the linear arc model. That we will look at all 3 eventually with data. But before you try to infer parameters from data, one important question is that notion of structural identifiability. So let me present to you how I think about structural identifiability. So to me, it all begins with a model prediction map. So that's a map, which in my case, I've written phi, T1, T7, and R. So T1, T7 are my 7 time points, and R is my number of replicates. And it takes a parameter in my parameter space theta and associate to it a point in 21 times R dimensional real space. Well, it's going to be in the real positive octant of this, obviously, because it's going to be the measurements of the 3 species S0, S1, S2 at 7 time points over 7 replicates. So this is my model prediction map. It takes a parameter and tells me what the measurement should be according to the model, supposing that we can measure exactly and what we're modeling follows exactly the model. So this induces an equivalence relation on my parameter space, which I'll denote by tilde and then T1, T7, R. And it's given by saying that 2 parameters are equivalent if and only if they have the same image under the model prediction map. So that, yeah, the model predictions are exactly the same for these 2 parameters. And so with this, I can then define identifiability. So given a model prediction map, I'll say that the model is globally identifiable if for all theta, the equivalence class of theta has size 1. So, or equivalently, the map phi is injective. And then we'll say it is generically identifiable if for almost all theta, the equivalence class of theta is equal to 1. And by almost all here, I'm thinking in a kind of algebraic geometric kind of way. So everywhere except in somewhere small. So there's 0 set of something small. And then locally identifiable will be if for almost all theta, the equivalence class of theta has finite size. So has finitely many elements. And then finally, generically non-identifiable if for almost all theta in theta, the equivalence class is infinite. So if you're in that final situation, even if a number comes out of your parameter estimation, you should definitely not trust it, because it's going to be so that there are, in this situation, there are infinitely many parameters in parameter space that gives you the exact same data. And so it does not make sense in that situation to perform parameter estimation. Okay, so what happens in our examples? So one thing that I want to note is that, so it says I defined this notion with this map, and now this map exists, at least in theory, but you cannot always get your hands on it because you cannot always have analytic solutions to your system, for example. But there are various methods for deciding whether to make some decisions about identifiability, and all of them assume the knowledge of the full trajectories. But thankfully, there's a nice result of Sontag, which implies that in cases like I have, so when your system is nice enough, then if you have 2m+1, so if you have perfect measurements at 2m+1 generic time points, you will have the same information as having the entire trajectory. And where m is the dimension of parameter space. So in my examples, I had dimension 6 for the full ERC model, dimension 5 for the rational ERC model, and dimension 3 for the linear ERC model. So 2 times 3 plus 1 is 7, which is exactly the number of time points I had. So that's okay, good. But then there's a big question is that this raises, okay, so if I have enough time points, I can hope they're generic and that they're good, but I cannot know for sure, or I don't know how to, I don't know, yeah, it's a big question. How do I know that I have good time points and I am really capturing enough? So in the case of the linear ERC model, as I've mentioned before, this one does have analytic solutions, and so you can write the model prediction map explicitly. And then you can we have shown that this map is injective for any choice of 3 distinct time points. So this tells me that this one is indeed globally identifiable. And we got our hands dirty and did the calculations. That one we know for sure. For the other two, we don't have analytic solutions, and so we cannot do the same kind of computation. And so we have to use some of the tools. There's a variety of tools available, and we picked the Cyan, developed by some of the organizers of this seminar. And using Cyan, we were able to show that these two models were generically identifiable. So the caveat is that this result also has some some assumption of things being generic, namely the time points, as I've just mentioned, but also the initial condition. But that we were able to deal with and show that our initial condition, because we had this very specific initial condition, we were saying S0 is 5 microgram and E is 0.65 microgram, and everything else is 0. So we had a very specific initial condition, but we were able to show that this initial condition is generic. What we don't know is whether we have enough or sufficiently generic time points. So we don't know, especially because we have so few compared to the size of the parameter space. So we don't know for sure if the result that we've obtained with this method actually applies to the specific experimental setup. But it is the best we have at the moment, and we have to live with it. So I think Daniel was saying that you've had a few talks about identifiability and differential algebra. So I will still come back and mention how it comes in, and I guess why I'm speaking in this seminar. So there's various methods, as I said, and there's a couple of methods that are based on differential algebra. So the one that we use, Cyan, which is by Hong et al. In 2019, and the older method by Daisy, which usually called Daisy, by Bellu et al. In 2017. And both these methods are different, but they rely on the same result, this differential Neustadt-Ansatz. So you place yourself in this situation that this big K is differentially closed fields, and in that situation, then there will be a correspondence between differentially closed subsets of Kn, so which are sometimes described as abstract solutions, and radical differential ideals in a differential ring, but also so-called analytic solutions, which are n tuples of analytic functions satisfying the systems of differential equations. So when I'm thinking about my my model prediction map, I'm very much here. And these two methods, that Cyan or Daisy, they play here in this world, in the differential ideal and differential, in a differential ring world. So let me just say a very brief, oops. So a very brief, a bit more. So if I have an ODE system of the form, so I've the form here, so x dot, so the derivative of x is a function of the parameter in x. I have initial conditions x of 0 is some x naught. And then this y equals g of x, that's what I can measure. So in my case, this was a subset of this. In my case, for the full arc model, this was a subset of the variable x's. And in the other two cases, it was everything. Then the differential ring in this case will be C round bracket theta of xy, so the polynomial ring in x and y and their derivatives with coefficients in the rational functions of theta. And then the differential ideal is the one generated by these two things and their derivatives. So x dot minus f of theta x and its derivative, well, each component of it, and each component of this one. And one notable thing is that in this situation, the ideal is, oh no, sorry, okay. In this situation, the ideal is prime, and so the quotient of my differential ring by the ideal is a domain. So Daisy looks at mostly generating sets, or not generating sets, it looks at this ideal directly, and Cyan is a little different. Okay. So Cyan will rely on the following key mathematical result. So if you take little k to be the subfield generated by the polynomial ring in y and its derivative, so that's just the measurable output here, then if k is equal to the field k when you adjoint the parameters, then the model is generically identifiable. And if the field extension is algebraic, then the model is locally identifiable. So in their paper, so this is in the paper of Ong et al. From 2020, and in this paper, so the notion of identifiability that's used is a bit stronger than, no, it is considerably stronger than the one I use, but it does imply mine. So this is very abstract and not yet quite a tool that one can use, but Ong et al. Do make this effective, and then also present a probabilistic version which can be used on what they call realistic models. And this is implemented in Maple. So my model, although it is the model that we looked at, are real model, but they're probably smaller than what they had in mind when they wrote realistic models, but they are real models that were studied in the lab. Okay, so now what, so we used this Maple implementation and put through these two models and found that they were structurally identifiable. As I said, with the caveat that perhaps our time points are not, maybe we don't have enough time points, or maybe they're not sufficiently generic. But there would be some choice of time points which would be for which this system would this result would apply. Okay, so now let me just look at the time. Yes. Okay, so this is all the very, so it is, so this is still very much detached from any kind of reality. So we're just talking about the identifiability of the model, whether in principle the data identifies the parameters. But so in Young et al., what they wanted to estimate the parameters. They had data from this and wanted to estimate the parameters and found, so the reason they went for a model reduction was that they could not, so when they tried to perform this least square approximation, which is what many people start with, they couldn't estimate parameters. So they couldn't narrow down the parameters. And so it didn't look like they could actually identify them in practice. So there is another layer of difficulty that happens when you start introducing some noise. And that's where practical identifiability comes in. So if you want to, so there is an intuitive notion, which is that you try to estimate the parameters and it doesn't work. But with my collaborators, so Heather Harrington and Dhruva Raman, we came up with a definition. So for my definition, I need to start with a model like I had before, with a model prediction map. And I need to know, or to make an assumption about the probability distribution of data with true parameter theta. And then I need the assumption that my model is generically identifiable. And so if I'm in this situation that I have the probability distribution and I assume my model is generically identifiable, then for a generic Z star, so that's a data point, so something, in my kind of case, it will be measurements, then the maximum likelihood estimate exists and is unique. So this is going to be crucial for writing down this definition. And then I'm going to need a reference metric on parameter space. So this is going to very often, this is going to be just the Euclidean metric, but you can probably imagine other kind of mathematical models where the parameter space naturally has a different metric that's not the Euclidean metric. So with all of this in mind, we can write down this beautiful, complicated definition. Well, beautiful, I don't know, complicated, definitely. So what we need first to define is these delta confidence region. So I've written it here. So it's U delta of Z star. So I put in the data point, and it's in terms of this little delta. And this is going to be the set of parameters such that the negative log likelihood of psi of theta Z star is strictly smaller than delta. So that's a confidence region for a likelihood ratio test. So that's the likelihood ratio test where the null hypothesis is that the true parameter is, say, theta 0, and the H1 hypothesis is that it's anything else. And this region, it's the set of parameters for which the null hypothesis is not rejected. Okay, so we end up with this thing. It's a confidence region inside of parameter space. And we'll say that the model is practically identifiable for data point Z star at a significance level alpha, if and only if the confidence region U delta of Z star is bounded with respect to the metric d theta, where delta is given like this. So it's the negative log likelihood of psi of, so this theta hat of z star, that's the maximum likelihood estimate that you get from the data point z star. And then I've got z star again, and got negative log of k star. And this guy, k star, is determined by the significance level alpha. So it's the probability. So alpha needs to be the probability that this thing is smaller than k star, where z hat is data with true parameters, this maximum likelihood estimate. Now, I don't expect you to get your head around this definition, and I wrote it down and I barely do myself. And as it proved when we started looking at this problem, is that this definition of practical identifiability, although it does make sense, and when you work with it a little bit, you really see why, it is not very practical at all, because getting the k star from the alpha requires understanding the probability distribution of this thing, which is not at all easy or straightforward. So it is a sensible definition of practical identifiability, but it is not a practical definition of practical identifiability. Okay, so let's try and see a bit in the specific case that we looked at. So in this specific case, we decided that the reference metric should be the Euclidean metric, just because it's a subspace of Rn, so that makes sense. And the measurement error we assumed was additive Gaussian noise with covariance a multiple of identity, and mean the image of the model prediction map. So this is a really big assumption, which does not make complete realistic sense, because the Gaussian distribution has infinite support. And so I'm going to pretend that it's possible for some substance to have negative moles, which is just not possible. But it does fit with what people are doing in real life. So when people are doing least square approximation, they are implicitly assuming that error is additive Gaussian noise with covariance a multiple of identity. So it is the same kind of assumption that others are doing, and it does make things much easier. And in the case of the linear ERK model, where we have an explicit analytic solution, so we have an analytic solution of the system, and so we have an explicit model prediction map. What you can do is, so it's hard to get your hand on the delta, but once you have the delta from my significance level 0.05, you can plot the boundary of the confidence region. And what is that boundary is the pre-image of some circle. So a pre-image of a sphere in data space, how it is deformed like this. And the thing to observe, so this, I look at this and I can tell you, it is practically identifiable because all of these potatoes are bounded. And if you have a look at the paper later on, you'll see there's a whole bunch about Bayesian inference, and then some topological data analysis of the point clouds that you get from performing Bayesian inference. And those point clouds are similar in shape to these potatoes, as one would expect. And we try to see what happened in the other cases. So let me show you one plot for the rational ERK model. So in this case, a parameter space is 5-dimensional, which is harder to describe. And so in this case, we've plotted marginalized confidence areas. So we've just have, okay, this is tiny, but we've got in this direction, this is the gamma 1. So in the vertical direction is gamma 1, and the horizontal direction is kappa 1. And they vary from 0 to 1,000. And we've plotted, so this is the plot for the confidence area for alpha equals 0.05. Now this one, because we don't have access to its analytic solution, we had to do numerically. So it is not a proof, but it's a very strong indication that this model, the rational arc model, is practically non-identifiable. And you would get some similar picture if you were to do the same for the full arc model. So we had this model, which, as I said before, is structurally identifiable, provided that my time points were good. But then as soon as I start adding some noise, that doesn't work anymore. So we cannot identify the parameters because it just isn't bounded. And so a question that becomes quite interesting is to understand where this non-identifiability comes from. So I've mentioned the time points a few times, so that those are a possibility, although some numerical experiments indicate that at least the number of time points is probably not the problem, because you can simulate with extra time points in the middle, and it still gives you this same kind of situation. But one thing that I think is very much interesting in exploring is the fact that, so this linear arc model that we get it from performing this quasi-steady state approximation. And it tells, and the fact that the quasi-steady state approximation is valid says that the trajectories of our original model are close to the trajectories of this model that has a parameter space of dimension 3. And so you should not expect from the data that fits this model to be able to determine parameters in a 5-dimensional space. At this point, this is very much just intuitive, but this is something that I'm interested in figuring out. And let me finish now by thanking you for your attention. I'll be happy to answer questions. And these are the 2 papers that I've mentioned. So the biology one, which appeared in Current Biology in 2020, and the more mathematical one, which appeared in the Bulletin of Mathematical Biology in 2022. So thanks.
Thank you very much for this very clear and interesting talk. And we have quite a bit of time, I think, for questions. So if you have a question, please just unmute yourself and just ask, or you can write in the chat. Maybe I start with one question. You had the definition of various notions of identifiability, like generic identifiability, local, etc. And then later on, you had the definition of practical identifiability, which somehow depended on a level alpha. Am I right in guessing that there's first of all no explicit, no direct implication of one of the identifiability notions of the first kind to the practical identifiability? Is there like an implication between any of those?
So when I defined the practical identifiability, I assumed that my model was already generically identifiable.
Oh, I see. Okay.
You could probably, because of the way that it's defined, you need the maximum likelihood estimate to be unique. Otherwise, some of this stuff, complicated stuff, does not make sense.
Yeah, I see.
So it does, yeah, you start thinking about what happens in practice. But I mean, it is, yeah, so I can imagine that it could make sense to have a practical identifiability that should be separate, but this is not the definition. That this definition can only work in a generically identifiable case.
I see. Yeah, thank you. That I didn't. I wasn't aware. Yeah.
And then the other thing that maybe I did not highlight this so much, but structural identifiability was something that was generically true. So it's almost in almost all of the parameter space, the situation is similar, but the practical identifiability is very much local. So it was identifiability at the data point Z star or near that Z star, and where you are, what kind of data you have determines the practical identifiability.
Okay, thank you. Other questions?
Okay, may I ask a question? So I guess for many models, some parameters are allowed to freely take different values. So maybe I don't know if this question makes sense. That maybe the identifiability is only for some parameters. That means that it's maybe the system is not identifiable for all the parameters, but if we can allow some parameters, I mean,
yes,
it's not identifiable, but only a small set of parameters are identifiability. I don't know if this makes sense for you.
Yeah, so I think you're talking about, yeah, so if you have a parameter that's a vector of numbers, and there might be some of them, some of those entries, yes, so there are some notions like this where maybe you cannot identify the whole thing, but some parts. And then there's also some other notions where, okay, maybe you cannot identify your parameters, so the entries of your vectors, but you can identify some functions of them, some parameter combination. So you could do a reduction that would be kind of exact, so a change of variables, and express your system in terms of these new parameters if you're lucky. So there's various levels of things. So yes.
Okay, are there any practical methods or algorithms to determine, I mean, which kind of parameters are likely to be identifiable? I mean,
yes.
Then I just focus on this kind of parameters to do the parameter estimation. Yes.
Yes, so Cyan will tell you which of the components are identifiable. If it runs through, it will tell you which ones. And then I think some of the same authors have developed some methods for finding the identifiable parameter combinations. But then there's also, the biologists have developed a lot of, they might know from other experiments that certain combinations are identifiable, and so they will try to get those combinations in there and express some other things in there.
Oh, okay.
So
okay.
There is both some theoretical or computational tools that can help you with this, but there's also the vast array of practical knowledge.
Okay.
And experience.
Okay, thank you.
Thank you.
Other questions?
Hi, I have a question about the quasi-steady state approximation.
Yes.
Does it sound, you kind of hinted this at the end, it kind of sounds very close to implying that something is definitely not going to be practically identifiable. Like the reduction kind of specifically shows that you can use a smaller set of parameters.
Yes.
I just want to understand the thing you said at the end. Were you trying to hint that there might be a theorem of the sort after you do a quasi-steady state approximation, the parameters you eliminated are no longer practically identifiable?
I guess it is a somewhat vague conjecture that like a vague conjecture that if if your data it's maybe the thing is it's hard to make it precise, right? Because practical identifiability is about practical identity at a data point, and the quasi-steady state approximation is it's valid at some parameters, so it's hard to match these things together. But somehow, if your data that's close to model predictions that come from those parameters where your quasi-steady state approximation is valid, then you should not expect your model to be practically identifiable near those parameters.
Another question, does the quasi-steady state approximation, oh, sorry, go ahead.
No,
does it come with quantitative error bounds? Like, are you able to actually quantify or at least bound how far it is from the model before reduction?
Yes.
I haven't seen it before.
I don't know in the general method, but in this algebraic quasi-steady state, they've made an effort to do this.
Okay.
Yes.
All right. Thank you so much.
Thank you.
Other questions? I had another quick one.
Yes.
Early on, you mentioned, maybe it was slide number 10 or so, you were able to show that certain time instances were generic. And maybe you said it and I missed it. Initial conditions.
Yes.
And so
because the result of that comes out of Cyan is valid for one generic initial condition, and what I have is one very specific initial condition. And so we had to look whether, if I look at this vanishing ideal of this thing, whether it gives me the whole ideal. And it did.
I see. I was about to ask how you prove it, and yeah, I see. Mm-hmm. Yeah.
Yes, but so we could do this with the initial conditions. We didn't know where to potentially start, where to even start to try and say something about our time points. So none of us are very knowledgeable in differential algebra. So
thank you. Are there other questions? This doesn't seem to be the case. So thank you very much for this very clear and interesting talk. And we thank Emilie again.
Thank you very much.
And we have a next talk already lined up in 2 weeks' time. So see you all in 2